Hey, it's me, Steve, and this is my third take because I keep running out of space. But anyway, there seems to be a misconception among people about the moon's gravitational influence during certain phases, and that's what I'm going to address here. This is going to address this very specific thing. Okay, I'm not going to go into eclipses in too much detail into orbital parameters. I'm not going into angular velocity or orbital velocity or angular momentum, or any of that other stuff because it's not relevant for this. All right. If something is to scale, it'll say it on the slide. If there's nothing there saying anything, it's not to scale. So I don't want any dumb comments about that. And scale isn't relevant here because, like I said, I'm not using velocities and momentum or anything like that in this. All right. This is just to illustrate something. All right. This slide here, Perigee, you see Perigee and Apogee. All right. Perigee, supermoon. Okay, a lot of people are familiar with this. The term was actually coined by an astrologer, not an astronomer, but it's been subsequently adopted. But you see something called a micromoon at apogee. All right, so the claim I'm going to address here is the full moon has a greater gravitational influence than any other moon phase. That is false. All right, the phase of the moon has absolutely nothing to do with how close or far it is from the Earth, all right? The lighted side of the moon is just the daytime side of the moon, just like it is on Earth. Photons, essentially, at our scale, weigh nothing. You know, it doesn't matter if there's a googolplex of photons reflecting off the moon. It doesn't matter because 0 times a googolplex is still 0. So that's not... So the phase of the moon is independent of how close or far the moon is. And remember, gravity, it's a function of mass and distance, all right? Now here, I've taken everything from NASA, all my pictures and all my data, and this is where I've pulled it from, unless it says otherwise. So you can just go back and look at that, but you'll see this is where I pulled my data from, okay? Now, here you have the moon and the Earth. Their relative sizes are to scale here, but their distance from one another are not. The Earth is 3.7 times, or around 4 times the diameter of the moon. All right? All right, so here we have semi-major axis, perigee, and apogee. Well, what are those? We saw those in the beginning. All right, the semi-major axis is the average distance that, I'm just going to say planetary body. I know the moon is a satellite. Potato, potato. I'm just going to say planetary for something that orbits something else in space. All right, 2 solid objects. Okay, so the semi-major axis of a planetary body orbiting another is the average distance. Perigee, the closest distance, and apogee, the furthest distance. Well, why is there this variation? Well, orbits are not circular. They're elliptical. And an ellipse is basically a conic section with an eccentricity between 0 and 1. I've addressed this in other videos, so I'm not going to go into it here. All right, so orbits are not perfectly circular. Okay, so the moon at its closest is 3 1/3 times closer than it is at its furthest. That's what the little 3 blue earths there I put in the middle to show you that 3 1/3 there. All right. So this distance changes, but so what does that have to do with supermoon and micromoon and all that stuff? Well, hold on a second. I got to explain something else. Okay, inclination in the ecliptic. The ecliptic is the Earth's orbit around the sun is also an ellipse. But that ellipse that it orbits on is referred to as the ecliptic plane. All right, and here is you're looking along that plane towards the Earth. This is not to scale. All right, and you can see not only are orbits eccentric, but they're also tilted relative to one another. And the red line here is the axial tilt of the Earth. Actually, this says 5.1 degree. That actually is 5.1 degrees. But this is the reason why we do not get a solar and a lunar eclipse every month. All right, and well, what happens when this? Well, if you have 2 orbits, and in this case the ecliptic versus the orbital lunar orbital plane, that means you have a line where the 2 intersect. And at the end of each line is a node. Here's the definition of a node via Wikipedia. And you have 2, the ascending and the descending node. Why do I mention this? Because I'm going to show you on a short time scale how the moon's orbit tracks with the Earth's orbit around the sun, and I'll get back to what that means. It does precess. There is some precession of the lunar orbit, and that's the time it takes for the ascending node to move 360 degrees relative to the vernal equinox, and that time period is 18.6 years. But here that's not relevant. So basically what that means is the ecliptical orbit of the moon, the eccentricity doesn't change, the lunar orbital inclination doesn't change. What changes is where perigee and apogee are. They kind of spin over a long distance. But I'm only going to be showing you within a few months here, so 2 decades is way beyond the limits of what needs to be talked about, but I just thought I needed to mention it and explain why we don't get eclipses all the time. Okay, now here's the model I'm going to work off of. We have the sun, the earth, the moon's eccentric orbit, and the earth's orbit along the ecliptic. And this is as if you're looking down at a line between Polaris and the North Pole. All right, and these yellow arrows are the relative motions of the planetary bodies relative. You have the moon relative to the earth and the earth relative to the sun. All right. Now, in this situation here, we have a full moon at apogee. And that's what's meant by a micromoon. Now, all these phases are going to be full moons. We only see one side of the moon, and that's because the moon, one orbital period around the Earth is equal to 1 lunar day. That's why we always see the same side, okay? Now, watch what happens with each of these full moon phases as the Earth moves in the orbit. And watch the orientation of the moon's orbit, too. Now we have a full moon at the average moon-Earth distance, or semi-major axis. All right, so we're getting closer to a supermoon scenario, but the moon was full before at its furthest point. See where I'm going here? Here you have the full moon between the average distance of the moon-Earth distance and perigee. So it's getting even closer to the Earth. All right, and here we have a full moon at perigee, and this is what is meant by a supermoon. Now, as you can see, you can have a full moon, and the moon will still be at different distances in its orbit, and distance, the moon will be at a further distance from the Earth in its orbit. There, that sounds better. So, a supermoon is not the same thing as a full moon. All right, you can have a super new moon. You just won't see it, but it's there. You can get a situation if the moon was in its present position as it is here, but the Earth was on the right side of the sun here instead of left, you would actually get a supermoon during the new moon because it would be at perigee. All right, so the phase of the moon has nothing to do with how close it is to the Earth. Hence, it has nothing to do with the gravitational influence. All right. And I'm not going to get into tides or anything here. That's a rant for another time. So what I've done here is I have removed the Earth and the Moon. Their orbits have not changed. I just don't want to distract you from what I'm trying to show you. And the sun's in the middle here. Now watch as the lunar orbit moves with the Earth as the Earth orbits the sun. Watch its orientation. This is initial. 1, 2, 3, 4, 5. That is tracking. That, when I spoke about how the moon's orbit tracks with the sun, this is what I meant. If you notice, the perigee and apogee always point to the same points in distant space. All right? They don't change as the Earth orbits, all right? And I think that's where people get confused. I think people think this is what happens, and this is not what happens, all right? Yeah, I had to move that down a little right. You're going to see a part get cut off, but you'll get the point. This is what doesn't happen. Initial. 1, 2, 3, 4, 5, and 6. All right. If this was the way it happened, in this particular case here, we have perigee on the right and apogee on the left in this final slide. And what would happen here is during perigee, we'd always have a super new moon, and at apogee, we'd always have a full micromoon. and that isn't what happens. Because in what I initially showed you how how the moon's orbit tracks with the Earth and the Sun. This type of scenario, it wouldn't be tracking. Okay, so this is not what happens, and I think that's what a lot of people get confused as well. So I just thought I'd clear that up, and just hopefully that helps you out. So I think that's it, and I hope you learned something. If you have any questions or comments, feel free to leave them below. I'll entertain any realistic comments that make sense and aren't bumper sticker slogans and random exclamations with nothing and other assorted stupid stuff. But anyway, that's it, and I hope you learned something.